And we're back with a short presentation on conformal mappings, which are mappings that have certain kinds of geometric properties, namely they locally preserve angles, and they're also locally invertible, which is an analytic property. In this presentation, we'll take a look at the theory, and in the next one, we'll take a look at some applications of these things. Let's get to it. Okay, so conformal mappings are mappings of the complex planes that preserve the angle of intersection between any two curves in their domain. Okay, so that's not just a local property, that's actually a global property, even though, of course, the intersection between two curves, that's something that's highly localized since it's a point, right? And that's the name. Conformal basically means, well, the angles stay conform to each other. Okay, so although this feels, and in fact is, rather geometric, and therefore also seems rather theoretical, conformal mappings arise in many natural applications, and we'll say a few words about that in just a minute. Namely, consider a fluid flow, so consider a water flow or an air flow. Fluids can be gases or liquids. And although fluids can compress and decompress, for gases that is part of the theory, because gases can be compressed and decompressed significantly. For liquids, sometimes you assume they're incompressible, which is not quite true, but it's a good approximation for many applications. But so, although those things can compress and decompress, there are microscopic ways in which fluids will not compress or decompress. And that is because very close to a point, pressure and flow velocity are roughly constant, because pressure and flow velocity, unless you've got a turbulent flow, I guess, and here's really where my knowledge of fluid dynamics also pretty much ends. But for quite a few flows, you assume that pressure as well as flow velocity are differentiable, or at least continuous, and if that's the case, then very close to a point, they are both roughly constant. And that means microscopically near that point, the fluid will expand or contract evenly, depending on whether the surrounding pressure is lower or higher than what's happening at the point, and the fluid will move steadily. And that means if we've got two very thin streams of dye that cross each other at that point, think of just dye in a stream of liquid and a stream of water, or also the kind of thing that you sometimes see in a wind tunnel, where you just put smoke into an airflow. So if we've got these two thin streams of dye that cross each other at that point, then the crossing certainly will be deformed over time. But because very close to the point of intersection of these two streams of dye, we only have uniform motion and uniform compression, decompression, the angle of intersection will stay the same. And presto, we've got that fluid flows are conformal mappings, at least something that should convince us that conformal mappings have something to do with fluid flows. Okay, we will analyze the conformal mappings in this presentation, and we will consider applications in the next one. So first of all, of course, we have to define these things. And a complex function f is called conformal at z if and only if it is analytic in a neighborhood of z and the derivative at z is not equal to 0. The function is called conformal on its domain if and only if it's conformal at every point in its domain. And of course, you immediately ask yourself, what does that have to do with angles? Well, informally, near a point z sub 0, we have that f of z is a0 plus a1z minus z0 plus the remaining terms, which are all quadratic or of higher order. So that would be the z minus z0 squared times the sum j equals 2 to infinity ajz minus z0 to the j minus 2. That's just because an analytic function locally is equal to a power series, right? But now for small z minus z0, the quadratic term is really, really small in comparison to the rest. That is something, just go ahead and plot x squared versus any straight line, right? And x squared goes into the origin horizontally. Straight lines with non-zero slope don't, which means that x squared, as long as you get close enough to the origin, which in this situation we can get arbitrarily close to the origin, we will have that the quadratic term is a lot smaller than the linear and the constant term. This is an argumentation that you very often see in the sciences and engineering. It's something that took me a while to really accept, but basically it's the fact that x squared goes horizontally into the origin and stuff of lower order does not. That makes that work. Okay, so it's very small in comparison to the rest, and in engineering or science, if something is very small in comparison to the rest, you often just drop it. And if you do that, then very close to the point z0 where we expanded it, the function f acts like a translation and a rotation. And of course, these operations don't affect angles. And well, that is a nice geometric argument. This is an approximate argument. This is, with apologies to my colleagues in science and engineering, it's probably a scientific slash engineering argument. In mathematics, we'd like to have a rock hard proof. That goes like this. You take a conformal mapping on a domain D, and we let C and D be two simple curves that intersect at Z0 in the domain D. Oh, you can see what I've done here. I've used the letter D twice. Give me a minute. And we're back. Well, this is easy to fix. I just don't give the domain a name because, in fact, I don't really need the name of the domain. Of course, I should erase the other D. Okay, but now. So the situation that we have is we have a function that is conformal on a domain. We don't give that thing a name right now. And we take two curves, two simple curves that intersect at a point z0 in the domain. And what I claim is that then the angle of intersection between the curve C and the curve D is the same as the angle of intersection between the image curves f of C and f of D. Well, in the proof, we let gamma be a parameterization of C, and we let delta be a parameterization of the curve D, because of course we get f of C by composing f with gamma, and we get f of D by composing f with delta. We assume that gamma of 0 is delta of 0 is equal to z0, so we assume that the parameterization maps 0 to the point that we want to analyze. And well, then if we write gamma prime of 0 in its polar representation as r gamma e to the I theta gamma, and if we write delta prime of 0 in its polar representation as r delta e to the I delta, then the angle between the two curves is theta gamma minus theta delta, and that's because this angle is the angle of the curve versus the appropriate translation of the x-axis, so that it's the angle of the curve gamma against a horizontal line through z0. Theta delta is the angle of the curve parametrized by delta against a horizontal line through z0, and that means the angle between the two curves is just the difference between the two angles that are measured against the horizontal. Sure. Okay, so now f composed with gamma is a parameterization of f of C, f composed with delta is a parameterization of f of D, and with f prime of z0, if we write that in a polar form as r0 e to the I theta 0, we have that f composed with gamma prime at 0 is f prime of gamma of 0 times gamma prime of 0, which is r0 e to the I theta 0 times r gamma e to the I theta gamma. If we put that together, we get that it's r0 r gamma e to the I theta 0 plus theta gamma. So the curve f of C at z0 has an angle theta 0 plus theta gamma versus the horizontal. And similarly, f composed with delta prime at 0 is f prime of delta 0 which is r0 e to the I theta 0 times r delta e to the I theta delta, which is r0 r delta e to the I theta 0 plus theta delta. So for the curve f of D, we have that the angle versus the horizontal at z0 is theta 0 plus theta delta. But that, of course, means that the angle between those two curves is the difference between the respective angles versus the horizontal. So it's theta 0 plus theta gamma minus theta 0 plus theta delta. And that gives us theta gamma minus theta delta. And that's the proof, because we've just seen that the angle between the original curves, which is theta gamma minus theta delta, is the same as the angle between the image curves, theta gamma minus theta delta. Okay, as some examples, the function f of z equals e to the z is conformal on all complex numbers, and that's because its derivative is e to the z, and e to the z is never equal to 0. The sine function is conformal on the complex numbers, except that we must remove the zeros of the derivative, where the derivative is the cosine, and the cosine is 0 at pi halves plus an integer multiple of pi, so that's what we'd have to remove there. And then we also have a function that we haven't talked about for a long time, because f of z equals z bar is not analytic, but it preserves the magnitude of the angle between any two curves, and that's just a geometric argument, because we remember that if we map z to z bar, we flip everything across the x-axis, and that's an operation, a geometric operation that certainly preserves the magnitudes of angles. But we've got to be careful, just like a mirror, an angle theta gamma minus theta delta above the x-axis turns into the angle theta delta minus theta gamma below the x-axis. So f of z equals z bar does not preserve the angles themselves. And mappings that preserve the magnitude of the angle between any two curves, those things are called isogonal. I hope I'm saying that right. Basically, that means that anything that is conformal is also isogonal, but we're only going to work with conformal mappings, so that's just a little bit of background vocabulary, nothing else. Okay, let's take a look at some more geometry. If f is conformal and has derivative at z0 being r0 e to the I theta 0, then we call r0 the scale factor. That's because r0 is the magnitude of the derivative at z0, which we know is the limit as z goes to z0 of f of z minus f of z0 divided by z minus z0, the whole thing taken the magnitude of. And that means that if you've got a short line segment of length z minus z0, and short then of course is again one of those things that depends on the context, but a short line segment will be mapped to a line segment of length approximately f of z minus f of z0, will be mapped to approximately something that looks like a line segment. It'll be bent a little bit, of course, that has length f of z minus f of z0, and that's approximately, as long as everything is small enough, equal to r0 times z minus z0, and that means that what originally had length z minus z0 is now scaled by a factor r0 in the image. Similarly, theta 0 is called the angle of rotation, and that's because, similar to the above, f of z minus f of z0 is approximately r0 e to the I theta 0 times z minus z0, and that means that if z0 again is z minus z0 again is a short line segment, then the image is also a short line segment, and because of the multiplication with e to the I theta 0, it is approximately rotated by that angle theta 0. Okay, so because of the magnitude of the because the magnitude and the argument of the derivative change continuously with z, at points near z0 the scale factor and the angle of rotation will be about the same as they are at z0, and that just reinforces that something that is a short line segment will be mapped to approximately a line segment again, because the scale factor and the angle of rotation are very close to the same, as long as we don't get too far away from the point that we're investigating. So that means, yeah, sufficiently small regions then overall are so that their images look approximately like the original regions, just scaled and rotated. Okay, we also would like to visualize that. Let's take a look at the function f of z equals z squared near the point 1 plus I. And here, let me explain to my computer that I trust myself. So if I stop this real quick, here's the point 1 plus I, and I just have a horizontal line and a vertical line. They intersect at a right angle, and we're going to go through the animation that is quite customary. Of course, z squared ultimately maps this over here somewhere, and that goes directly. But if I go from z to the 1.01 to the z to the 1.02 and so on, I actually get sort of like a fluid flow, a continuous deformation. And what I want us to observe is that as we go through that transformation, the angle at this point stays a right angle, and that's the idea behind a conformal mapping, if you will. The idea of a fluid flow is that from time t equals 0 to time t equals whatever, it's always a conformal mapping, which is nice, but that means that at every point in time, the angles between intersecting curves are being preserved. All right. Well, let's take a look now at the local invertibility, and here's where we're actually going to dodge one bullet. We take a conformal map on an open domain, and we let Z0 be in the domain, and W0 to be f of Z0. Then there is a neighborhood of Z0, so that f has an inverse G on this neighborhood, and this inverse is conformal to, and its inverse at W0 equals f of Z0 is G prime of W0 equals 1 over f prime of Z0. That is something that you may also recall from calculus. That's just the formula for the derivative of the inverse, and well, because in many ways complex analysis, of course, extends what's happening on the real line, it shouldn't be too surprising that that formula works out. What is surprising is that existence and differentiability of the inverse are a consequence of the inverse function theorem, which is something that is rather technical, and so we're not going to prove that here. If you're interested, again, a small commercial here, permit me that joke, in my analysis book, it's corollary 17.66, and if you want to be really technical about it, you need just about everything we have derived up until that point in order to fully understand the proof of the inverse function theorem. And so that means, yeah, it is quite technical. So see that for details if you're interested, if you like that kind of theory. I don't care if you use my book or somebody else's, but you'd need a text on real analysis on that. Okay, so that leaves the formula itself, and the formula itself is not that bad, because as soon as we know that the inverse G is differentiable, we just take the derivative of the composition of f with the inverse, and that's the same as the derivative of the function w. So that means on the left side we get the chain rule f prime of g of w times g prime of w. On the right side we get 1 by elementary calculus, and that gives us that g prime of w is 1 over f prime of g of w, which is 1 over f prime of z for any z that is being mapped to w. And so if you stick indices 0 on there, you get the formula that we have claimed. So that was actually rather quick, but remember, there is an elephant in the room, if you will, a big and very beautiful piece of the theory that we left out at this stage. Okay, so let's now take a look at one quick example, which will look terribly elementary compared to what we have done in some of the presentations that were before this one. But now that we have the formula for the derivative of the inverse, we can verify one more time how the logarithm differentiates. And so by the preceding theorem, the logarithm is conformal on its domain, no matter which branch we choose. And at a point w equals e to the z, we have that the derivative of the logarithm is 1 over the derivative of e to the z, which is 1 over e to the z, and that's 1 over e to the ln w, which is 1 over w, which is the derivative that we know the logarithm to have. It's 1 over w. Okay, well, and that's it already for conformal mappings. Enjoy the homework problems on this stuff, and I really mean that. I would think that they should be refreshingly like calculus, and I think we've earned that because we've done a lot of rather complicated, complex analysis leading up to this stuff. And I'll see you with the applications where things will get a bit more technical again. See you there.